Meeting is being recorded.
Ooh, okay. All right. So today we have Fabio Mantegazza, who will tell us about rank 2 matter tensors and dualities. And he will draw an atlas for 3D n equals to 2 theories. Take it away.
Okay, thanks, Julius, for a nice introduction. First of all, I would like to thank the organizer for inviting me, for giving me the opportunity to talk about my works that are made in collaboration with Antonio Moriti and Andrea Zanetti from the University of Milan, and with Simone Rota from Sissa. So, as the title says, I will speak about 3D dualities in n equal 2, and in particular, as all we know, duality is an equivalent description at low energy of different quantum field theories in the UV, so at high energy. And what we are facing in the last decades is that dualities are not mere coincidence, but seems to be more structural features of supersymmetric quantum field theories, where with structural features, I mean that we have a systematic way to construct them by using more fundamental building blocks. And this constructive way of building dualities is not just specific to some kind of theory, to some kind of theory of a specific gauge group, or to some kind of dimensionality, but span a range of theories in which the application is very similar for all of them. So, as I said, my talk is in 3D, and but I would like to take a little step back, and indeed in 4D, this some step towards this systematic way of classifying theory was made already 30 years ago for the classification of S-confining theories with vanishing superpotential with minimal supersymmetry, and was made by Chucky, Smarts, and Skiba. And after that, there was a lot of work, and some years ago, we were able, I mean, not me, but Bejo and Benvenuti were able to prove these S-confining theories by assuming just some building blocks that are intrigator Pouliot and cyber duality, the S-confining limit of these theories. And then this method was generalized by Bottini, Juan Pasquetti, and Sacchi to construct dualities from dualities. In 3D, the situation is different from 4D. There are the theories are less constrained because there are no global anomalies. There are additional features in these theories. There is presence of Chern-Simons terms. There is an additional symmetry, which is the topological symmetry. And there is the most important thing is that there is not just the X branch, but there is also the Coulomb branch. All of these differences make a classification and a systematic approach to this kind of theories a bit more complicated to make. And but since we are facing a different situation where we can also look for a new feature for this duality. So what we can look for example, that is missing in 4D is the presence of symmetric tensors and monopole operators in this theory, and we can claim and we can try to obtain new theories, new confining theories, new dualities that are not present in 4D. So it is a very nice environment in which looking for different features for duality. So let's give out the plan of the talk. At the beginning, I will introduce some toolkit that we use in 3D n equal 2, and I will review some feature of the Coulomb branch. I will give some notion about the squash respiration function, and in particular, I will introduce an identity at the level of the constituent of this partition function, which is called duplication formula, that will be used in a massive way in this talk. And after that, I will review really fast the tensor deconfinement technique, more from a historical perspective, maybe. And after this, I will proceed to give two explicit examples taken from my papers. And in the first one, I will show how to use the duplication formula to construct a new duality involving a symmetric tensor. And in the second one, I will show how to convert the gauge groups. After that, I will conclude with some conclusion. So let's start if there are no questions about this first part. Okay, I will start with the introduction of the Coulomb branch. In particular, in this talk, I will not turn on Chern-Simons, and we will see how the presence of matter will change the Coulomb branch. So, but let's start with the Coulomb branch without matters. In general, we know that in 3D n equal 2, there is a scalar in the vector multiplet that is charged under the joint of the gauge group. So we can give a web to the scalar, and in general, this web to the scalar will break the gauge group to the maximal abelian subgroup. For example, for the case of SUN, we can break to the U1 to the n-1. So we know also that in 3D, for every U1 of the theory, for every U1 gauge, we have a topological symmetry associated because there is the existence of the dual photon that enjoy a shift symmetry, a quantized shift symmetry that will carry this topological symmetry concept for Bianchi identity. In general, so we have a topology of the moduli space that is R times S1, and we can parameterize this modular space at classical level by introducing some coordinates that will take in account both the web to the scalar and the dual photon. And in general, it can be shown that these coordinates that we are using at low energy to parameterize our moduli space correspond to insertion of monopole in the U theory. So with a little bit of stress, we will call these coordinates monopole operators. So, but this was a picture without matter. With the presence of matter fields, the story changed a little bit. Now we have fields, we have direction in the Coulomb branch in which the mass of some matter field can vanish, and when this matter vanish, we can have an intersection between the Coulomb branch and the X branch, because there where the mass vanish, we will have a massless fields that will acquire can acquire web, and this will place us in an X branch. In general, so we don't have a continuous description of the Coulomb branch, because at the intersection, the charge of the monopoles will jump, because we'll review in a little bit that how monopoles acquire charge, but in general, trust me, there will be we will not just a single continuum monopole to describe this Coulomb branch, and we will have to introduce a combination of them. And this was still classical, but now we have also quantum effect apart from the presence of matter effect. And in particular, we know in general that in absence of matter, there is an instantonic generation of a superpotential that will lift the Coulomb branch. In general, it will lift completely the Coulomb branch. In general, this instantonic generation of the effective potential, superpotential, has to do with the zero modes of the fermions in our theory. And when there is matter, this counting of the zero mode can change. So what can happen is that that there is an interplay between two scales, the monopole scales that is induced by the breaking of the SU2 that we are probing, by the breaking of the SU2 that it is breaking because we are giving web to the scalar in the joint, that is counting the instanton, and then between the mass of the fermions. In general, when this scale of the monopole will be associated scale to the monopole will be smaller than the mass of the fermion, this fermion will not affect the superpotential because they will be integrated out before going to the low energy. But when this mass will be, when this scale of the monopole will be bigger than the mass, we will have to take in account these fermions, and the counting of the zero mode will change. This is a long story, but to make it short, I can resume what Integrator Cyber did in the paper back in the 13. And so there are different directions that remain unlifted in the Coulomb branch. And in particular, when there are just fundamental, we have this diagonal breaking that will break our SUN. I will review in the following in the next slide. Will break the SUN to SUN minus 2. And we will have this combination of monopoles that will parameterize our Coulomb branch. In presence instead of an anti-symmetric field, the Coulomb branch will remain unlifted in different directions that are parameterized by the breaking that I shown here in the slide, and we will have different monopoles that will parameterize this unlifted direction of the Coulomb branch. Just to be clear, in my talk and in general in all the paper that we made, we needed just to consider the monopole associated to the fundamental breaking. That is the one that gives this breaking pattern in which SUN is broken to SUN minus 2 times U1 times another U1. And this was kindly shown also in a paper from Kitani in 19, where he was analyzing confining theories in 3D in presence of tensor. And what he noticed is that even in the theory where he could write in the low energy effective potential, in the low energy effective theory, monopole associated to the anti-symmetric breaking, you could rewrite this monopole in terms of fundamental monopoles. So what we will just need in this talk are these fundamental monopoles. A last thing that I would like to stress is that monopoles can acquire charges quantum mechanically. This is due to a one-loop mixed Chern-Simons term that arise when we integrate out massive fermions. And so, in general, these monopoles will not be always gauge invariant, but we will need to address them. So, in order to parameterize the Coulomb branch, we need the gauge invariant operator. When we go to low energy, integrate out some fermions, they acquire charge, and so we have to change this monopole by multiplying them for some field. And here I can be more explicit, in particular in presence of fundamentals or anti-symmetric. The monopole will not be gauge invariant if the theory present is chiral. So if the would-be content of the 4D theories is anomalous. And this is nicely seen from equation 5, in which I wrote down explicitly the charge of the monopole under the U1 gauge group. And we can see that in the square bracket, there is the cancellation of the anomaly for D. But with the symmetric fields, we can experience a new feature. Indeed, in the square bracket, there is no more the would-be cancellation, the cancellation of the anomalies in the would-be for the theories, and we can have monopoles that are not gauge invariant also for a chiral content of our theory. In general, so in the most of our example, we will have to trace this monopole to describe the low energy theory. So another toolkit that I would like to introduce is the SQUASD free sphere prediction function. And so it is a prediction function written localized on not an S3, but on a SQUASD free sphere that is preserving a one square isometry. And this allows us to write the content of our theory in the form that I pointed out in equation 9. And in particular, we can see that there are different contributions in this equation. First of all, we have an integral that is performed over the sigma variables that are the real scalar in the vector multiplet of n equal 2, and so we are integrating over the Cartan of the gauge group. All the integral is scaled after this by the Weil symmetry of the Cartan. Is normalized, sorry, not scaled. Then we can see that in the integral appears hyperbolic gamma function, in which the argument are the weights of the representation of the gauge group under which these fields transform, and the weights of the global symmetry of these fields. And in the denominator, we have the non-zero root of the vector multiplet. So the last thing that I would like to point out about this formula is that the one-loop determinants for the fields are rewritten in terms of hyperbolic gamma function, which I give the definition here. Is not very important, this definition of the hyperbolic gamma function, but what is important is that we have them in our theory. And in the next slide, I will explain why. In our operation function. So let's state lastly the convention that I will use in this talk. In general, I will not write when there is a gauge theory, the explicit operation function, but I will use a shortcut, and in particular, I will synthesize the matter content of this theory with the fundamental mu. I will summarize the presence of the fundamentals with an associated parameters called mu, the anti-fundamental with nu, tau s and tau s tilde for the anti-symmetric and the conjugate, and tau a and tau a tilde for the anti-symmetric and the conjugate anti-symmetric. Tau s for the symmetric, sorry. So I was saying that the important point is that in the integrand, we have the presence of the hyperbolic gamma function. And this is important because this function enjoys some nice properties. In particular, there is the reflection formula that is used, that implements at the level the operation function, the integration of a lagomorphic mass term, and is useful for what I will call flipper in the deconfinement technique. I will explain what they are in the second part of the talk during the examples. But I can explain here what this very simple formula does. In particular, if we take a theory, here I just take a very schematic theory in which are present just two singlets, A and B, and we turn on a mass we turn on a mass interaction for these fields, and at the level of field theory, we can do the F terms and integrate them out. At the level of the operation function, this integration out of this field is seen from the reflection formula. Indeed, the superpotential will constrain their symmetry, the sum of their symmetry of this field to be 2, and in the reflection formula, this is taking account by 2 omega. So when we see that 2 hyperbolic gamma function, the argument of 2 hyperbolic gamma function sums to 2 omega, it means that in the superpotential it is allowed a mass term, and so we can integrate them out. And this integration is correspond to putting the multiplication of them to 1. This is more very known result. Maybe a little less known identity is the duplication formula that I wrote in this slide. And it is useful when we want to convert some tensor field, for example, an anti-symmetric tensor field, to a symmetric one at the level of the operation function. This will be the main topic of the first example of the talk. The other very useful application of this formula is that it allows to convert the gauge measure that is in the operation function of a symplectic group to orthogonal groups. This was made clear by an article by Benini, Closet, and Cremonesi in 2011. And this will be the main topic on the second example of the talk. One thing that I would like to stress here is that this formula does not have an obvious physical interpretation and it does not always work. This means that when we are able to use this and to interpret from the operation function the field theory, we are happy, but this is not guaranteed a priori. So let's maybe, before going to the two examples of the talk, make other two examples in which I can show the application of this duplication formula. In particular, in this example, I will consider an SUN gauge theory with an anti-symmetric with fugacity tau, and for fundamentals mu1, 2, 3, and 4. What we can do now is freeze the four masses. Here I use the term freeze by renting terms that he used more from the brain's perspective, but I will comment this in the conclusion. So we can set the values of these fugacities to some precise value in order to use the application formula, and we can read after the application formula what the one loop determinant of our fundamentals will become. And in particular, it is done in the equation 14. And on the right-hand side, we can see that the four fundamentals give rise to the missing contribution to the one loop determinant that would make an anti-symmetric field a symmetric one. So we are creating what convert an anti-symmetric, an hyperbolic gamma function associated to an anti-symmetric field in an hyperbolic gamma function associated to a symmetric one. The other example is can be made by freezing just three of the masses. So we can set three values of the fundamentals to the values explicit in equation 15. We can apply the application formula, and we can see that we are still creating the missing contribution that convert the hyperbolic gamma function associated to anti-symmetric in a symmetric field, but also we are creating an anti-fundamental field that has the right charges to be compatible, to have a superpotential, a cubic superpotential with the symmetric. So in general, what we will do, what we have done in the paper and what I will do in the talk is that when I apply the application formula and I will see from the partition function this hyperbolic gamma function, I will know that in the superpotential there will be this kind of interaction. So before going to the example taken from the paper, I would like to give a very fast review of the technique called tensor deconfinement. I will use that in the example, so I will not make any explicit case, but I would like to stress maybe the main point that led us to this technique. It is a very old idea, is date back to the 96 and 95, when in the first article by Berkutz and Lewis, Maltz, Sterling, and Pouliot, in which the idea was to try to construct dualities in presence of tensorial metric field, and this was done by deconfining this tensor. That means trading the tensor with additional degrees of freedom, and in particular with additional gauge nodes. This was then interpreted in a more modern way in 3D n equal 2 by Pasquetti and Sacchi in 19, in which they introduced this technique for these theories, and after this it was still used in 3D n equal 2 by Benvenuti, Garozzo, and Monaco. After that, we had two very important developments made always by Benvenuti and Bottini, Pasquetti, and Sacchi, in which we were able to apply this technique in 4D and prove the S-confining theories for USP, for the symplectic and the unitary groups, and in general, generalizing this theory also for other dualities, not just for S-confining theories. And we were able to prove these theories by using just some building blocks that are the S-confining limits of cyber-integrated Pouliot dualities in the case of Benvenuti, and then to use just the cyber-integrated Pouliot dualities for the case of Pasquetti, Bottini, Wang, and Sacchi. So now let's introduce what is the main topic of the first main topic of the talk. So we know about a classification made by Keitani in 19 of S-confining theories for unitary and symplectic gauge groups in presence of anti-symmetric matter tensors. And this was already done. One question that we can ask now is, can we use the application formula on this theory in order to obtain new conjectural dualities or in this sense, new conjectural confining theories by this classification? This was the main question that we asked for the first article, and the answer is yes. And in general, as I already said a lot of time, we have these confining theories that were investigated by me, and in general, they are associated to an integral identity at the level of the evaluation function. We can start now from the evaluation function, apply the application formula, convert the contribution of the hyperbolic gamma function to the integral and to the singlet content, and reread from the evaluation function, which is the new conjectural duality. At this point, we can interpret this at the level of field theory and try to check this. The first non-trivial check is that is an operator mapping between the baryons, the mesons, and the monopoles of the theory. In particular, what they were the gauge singlet of the starting theory will be the new gauge singlet of the new conjectural confined theory, and a non-trivial map is to check that they are indeed the right gauge singlet of the left-hand side, of the new left-hand side. And after this, we can support this conjecture by a more field theory analysis by using the confinement. So if everything is clear, I would be very explicit with an example. And this is taken from my paper with Antonio. And I also use this example to set the notation. In particular, I will use I will use red circle to denote gauge node. I will use black square to denote the flavor symmetry, and in general, I will write the rank of the flavor symmetry inside this black rectangle. And for me, arrows are bifundamental fields. Fundamental when they go out from the node, and anti-fundamental when they enter the node. And then I will denote the tensor and matter field with the associated Young tableau and an arrow connecting it. And in general, every quiver will come with the associated superpotential. So we can read from the quiver what kind of theory it is. It is an SUN gauge theories with 2n minus 1 anti-fundamentals for the gauge group and 3 fundamentals and an anti-symmetric tensor. This was studied again in Keita by Keitani in 19, and it was claimed to be confined in terms of the gauge invariance made by the mesons, the baryons, and the Pfaffian, the anti-symmetric. In general, this theory, as I said, we are in 3D n equal 2, so we should not be surprised that in the low energy action, the low energy superpotential will appear a monopole superpotential, terms. And indeed, it appear a monopole operator that will act as a singlet in the confined theory. And we can read the associated identity at the level of the partition function in 18, and we can read from the left-hand side the matter content of the quiver, and from the right-hand side the matter content of the gauge singlet of the theory. So we can now just focus on this partition function, and we can apply the application formula. And I will do a freezing in which I will freeze just the 3 fundamentals, because are the only one that are available here. And I will set them in the values that I wrote in the slides. I will also rewrite the fugacity associated to the anti-symmetric with a label for the symmetric, because we already know that the anti-symmetric field will be converted to a symmetric one. So on the left-hand side, we can read the new theory. It will be always an SU2N gauge group. It will have a new anti-fundamental fields, and the other 2n minus 1 anti-fundamentals will still be there. And instead of the anti-symmetric field, we will have the symmetric one. On the right-hand side, we can see how the different singlets will be converted in the new confined version of the theory. So let's read from the partition function the matter content of the new conjectural duality, of the new conjectural confining theory. And so, as already said, there is these new anti-fundamentals that has the right quantum numbers to interact with a cubic superpotential with the symmetric, and the other anti-fundamentals were still there. For the magnetic theory, we can read from the partition function that the gauge singlet are the determinant of the symmetric tensor. This let's say, baryon operator, and two monopoles. Here, I would like to point out that we have two different monopoles, because both the fundamental is gauge invariant, but also addressed version of this monopole is gauge invariant. And indeed, they will appear in the superpotential because they have the right charges to be there. So we conjecture from this identity at the level of the partition function that the theory that I just showed will confine with this gauge singlet and will create this superpotential. We can support this claim by using the tensor deconfinement, and indeed is what we did. So let's introduce the starting building block, and so that I can also review a little bit the tensor deconfinement technique. So this is a confining theory that we know is confining from a paper of Benvenuto and Monaco in 21. And it is an SU2N theory with one symmetric and one anti-fundamental with this cubic superpotential. Sorry, this is not the confining theory. The confining theory is the SO2N theory with 2n plus 1 fundamentals. This is the confinement. So we can trade the symmetric tensor with additional degrees of freedom. That in this case will be the one made by the SO2N gauge theory with these 2n plus 1 fundamentals that we know is confining from the paper of Benvenuto in Monaco. And here I added on the right-hand side some what I would call flipper fields that are fields that will allow us when when we are going to reconfine the node to show this tensor deconfinement to get rid of all the unwanted auxiliary degrees of freedom that we introduced. We can read also the duality mapping of this building block, and we will have the generalized symmetric tensor and the generalized values. So we can apply this building block at the starting theory, and so we can trade the symmetric for this additional SO2N gauge group, and in this deconfinement will appear the monopole superpotential associated to the fundamental breaking of SO2N. Usually they are 2 because they are charged under a Z2 symmetry. It will appear just 1 because the other one is not gauge invariant. So the duality mapping is the same as before, but now we note that the special unitary group has 2n fundamentals and 2n anti-fundamentals, and we know that this is a confining theory. It is the confining limit of S plus D in 3 dimension, and it will confine in terms of monopole operators, baryons, and mesons. In general, here, the monopole operator will enforce the classical constraint on the modular space of S plus D. So we can use this building block in the theory, and we can confine the SU2N gauge node, and so get rid of this additional node, and we get the right-hand side, in which from the duality mapping, we can read the new field, and we can notice that there will be some mass terms because relating some mass terms involving the new fundamentals and anti-fundamentals of the theory and the new singlets of the theory. So we can integrate out these massive fields, and we obtain the theory in the first quiver of these slides. Here I have to point out that there is a dynamically generated terms in the superpotential. Indeed, from the duality and in general from the integration of this massive term, the term is in green in this superpotential will not appear. It involves interaction between a monopole and a baryon, and this is read from the quantum numbers of these fields, and we claim that is generated in this step. After this, we can again notice that this is the confining block of Benvenuto in Monaco, so orthogonal group with rank 2n and 2n-1 vectors, and we know that is confining, and in particular it will confine in terms of symmetric and baryon monopole. So we can effectively confine this theory, and we can obtain, after all this chain of dualities, the claimed confined version of our initial theory. From this potential, we can map the various field to the one that we claimed at the beginning, and we see that there is an agreement between what we claimed were the quantum numbers and what we claimed were the superpotential between the final theory that we find after all these steps of deconfinement and reconfinement. So this was for rank 2n. For the odd rank is completely analogous, and in particular, this kind of analysis was performed in this article of me and Antonio of the last year. And in this article, we were able to prove the confinement of all the theories that I listed in the slides, which are obtained by the classification made by me in 2019. So this is the first main result, obtaining a new classification of confining theories in presence of symmetric tensors. And the analysis is completely analogous to the one that I just performed. After this, I can move to the second example of the talk that will revolve more on the paper that came out last month with Antonio, with Simone and Andrea. And in this work, the starting point was in 4 dimension, and in particular was a self-duality claimed for 4-dimensional theories. In particular, it involves a special group with 2n rank, an anti-symmetric matter field, and a conjugate anti-symmetric field, and 4 fundamentals and anti-fundamentals. This was claimed in the article by Chucky, Smaltz, Skiba, Terning, and Spiridon and Bartolo at the level of the superconformal index, and it was proposed to have a symmetry enhancement by Razan, Matsela, and Zafrir in 17 and 18. We tried to prove this self-duality, and we succeeded for low rank, for SU4, a proof by tensor deconfinement, so in a very similar way to the one that I proposed before. But we didn't succeed in generalize the kind of the confinement that we use for SU4 to the general rank. But in trying to generalize this the deconfinement procedure, we noticed that there was a phase of the chain of the confinement that we used that was interesting by its own, because if we add a baryonic dangerous irrelevant operator to this phase, we can trigger an X mechanism on the dual gauge group and break the special unitary group to a symplectic one. After this, we proved via tensor deconfinement these new conjectured dualities, and we decided to reduce this theory from 4D to 3-dimension. We obtain new confining dualities in 3-dimension. We proved them also the level of tensor deconfinement, but maybe what is most interesting is that this new identity came with an identity at the level of the operation function. We manipulated the operation function to convert the symplectic groups to special orthogonal groups, and we claimed new dualities that we proved via tensor deconfinement. So let's review very fast what we did, also because I think that this is going towards the end of the talk. So this was the confinement, the sequence of the confinement that we used in for proving the self-duality of SU4, at least for one phase. For the other phase is a different confinement, and it revolves around the fact that for SU4 we have that the anti-symmetric representation and the conjugate one are basically the same. There is no distinction. And so we can make this double deconfinement that will not change the structure of the quiver, but will change the singlet content in the theory and give the right superpotential for the phase. I don't want to enter in the detail of this, but what I would like to stress is that the first line of this sequence of the confinement is common also for the general rank of the gauge group, and we can reproduce this for the general rank. So I give here the general structure of the quivers and the superpotential. We can read the duality mapping from the slide. In particular, I would like to stress the duality mapping of the operator of ρ1, ρ2, and ρ3 that are indeed the baryonic dangerous operator that we will add on the left-hand side in order to trigger the DX mechanism. Indeed, if we add, for example, a tilde to the power of n minus 2 q tilde to the power of 4, we will map this term on the right-hand side to a linear term in the superpotential that will trigger a non-trivial bev for the anti-symmetric that will trigger an X mechanism for the SUN group, so that will break the symplectic group. So we can do this even for even rank and odd rank, and for all the possible deformation that we can map. And in particular, the general outcome will be the one that I depicted here in the slides. And from SUN theories, we will go in general to symplectic one with anti-symmetric and 8 fundamentals, and with a different rank depending on the baryonic dangerously relevant operator that we add. This is also true for the odd rank, but there we just had 2 operators that we can add. So now we have these 2 new dualities involving a special unitary group and a symplectic group. We can read the identity at the level of the Fourier function that comes from the reduction of this duality from 4D to 3D. And in general, we will have an identity at the level of the Fourier function that comes with 2 constraints. One is enforced by the superpotential, and the other one is enforced by the KK monopole of the 3D direct reduction. So we can proceed in the same way as before, taking this identity at the level of the Fourier function and apply the freezing for 3 anti-fundamentals, and convert, first of all, the anti-symmetric field in a symmetric one, but this time we will also convert the gauge group of the right-hand side to that is symplectic to an orthogonal group, and we can read the new matter content from the variation function. I point out that also the balancing condition that constrained this identity will be mapped to new balancing condition in the new theory. So we can read the electric side and the magnetic side associated to the new identity at the level of the variation function. And in particular, on the left-hand side, we will have a gauge theory with a gauge group SU2N, and with an antisymmetric and a conjugate symmetric field with 5 fundamentals and 1 anti-fundamentals. In general, one of these fundamentals will interact with the conjugate antisymmetric field in a cubic way. On the right-hand side, we can read the claimed dual, that is an SO2N theory with an antisymmetric and 5 vectors, and a some terms in the superpotential that involves the monopole of the fundamental breaking and interaction between the singlets of the theory. So we can try to prove this theory again by the confinement. Here I will be faster than before. And so I will use these two building blocks, these two confining theories. One is SON with n+1 vectors, and the other one is a symplectic group with 2n+4 fundamentals, basically the reduction of the intricator-Pulio confining theories. And so we'll apply these confining theories, and we can use them in reverse in order to deconfine the conjugate symmetric and the anti-symmetric tensor matter in this double deconfinement. We can read from the mapping of the confining theory the duality mapping, and in particular, we will introduce new fundamentals and new baryons to the theory. After this, we can notice again that the SU2N group has 2N fundamentals and anti-fundamentals, and this is the confining building block that I showed in the middle of the talk. And so we can confine this node. This will generate what I should stress now, that I forget in the first slide, is that this deconfinement breaks the SU4 flavor symmetry to a 3 plus SU3 times 1. This breaking is just in order to use this deconfinement, and indeed at the end we will see that we will restore this SU4 global symmetry. So after confining this SU2N theory, we can notice a lot of interaction in the superpotential. I don't want to be a lot technical, but we are left just with two gauge groups, special orthogonal groups, and a symplectic one. And in general, we can read also the mapping of the various mesons, baryons, and antibaryons of the theory. So now we can notice that the symplectic group has 2n plus 2 fundamentals, and so it is the confining limit of S plus D with USP with the symplectic group, and we can confine again this gauge node. What we obtain in this confinement is the special orthogonal gauge group theory with an anti-symmetric and 5 vectors. Here we are still the flavor broken, but after the integration of the matter field, we can notice that we can restore the SU4 symmetry that we broke at the beginning with the confinement by reading from the superpotential the interaction that are preserving the SU4 symmetry. And so we can restore at the end the final quiver and the right claimed duality with all the interaction. So I would like to conclude the talk by repeating the main result that we get from this kind of procedure. And in particular, what we did was to try to give a new classification of confining theories and dualities in 3D. It's not complete, but it is constructed in a systematic way from known dualities and from known confining theories. And in particular, this approach revolves around the fact that usually dualities comes with an identity at the level of the partition function, and we can use exact identity of the constituent of this partition function in order to manipulate this identity and to convert them to other theories. We can read, so from the partition function, this kind of the new conjectural duality and the new conjectural confining theory, and we can try to interpret that at level of field theory. After this, we can support this new claim by a field theory analysis that involves tensor deconfinement technique, and in general all the recent developments in the context of dualities from dualities. And this gives us a systematic way of constructing these new theories. What I would like to leave as probably the main outlook of this kind of work are not a lot of technical question, but maybe a more general question that we have technical we know at a technical level when this duplication formula fails, why it fails, but we don't have any kind we don't have an interpretation from the level of brain engineering of this kind of move at the level of the duplication function and at the level of field theory. So it would be nice, if not with more supercharges, it would be nice to have an interpretation of this kind of construction also with minimal supersymmetry. And with this, I would like to thank you.
All right, let's thank Fabio. Do we have questions? I think it was very clear. In that case, I would say let's thank Fabio again immediately. And we can move on to the informal part of the record.